Are you guys ready?
Yeah, let's do it.
All right, cool. Okay. So, so last lecture on Tuesday, we learned about this concept of exothermic reaction, endothermic reaction, and then my takeaway slide is this one, which kind of summarizes what happens in an endo and exothermic reaction. And then we just got introduced to the concept of an energy diagram, which, as the name suggests, is nothing but a graphical representation of the different energy levels of the reactants and the products. So far, so good? Okay. So not really going into the details of what's happening. You guys can read some of these slides, but I really want to kind of highlight some important things. So reactions happen when you know that molecules or particles kind of collide with each other, and that's how you kind of they are always in this random moment, right? And that moment is what the kinetic energy is associated with in terms of the movement of the particles, right? And when these particles are colliding with each other, they transfer the energy. And then you also know that as electrons are going from the outside and on the outermost level, they're trying to get to the lower state of stability. So when you talk about stability, it automatically associates with a lower level of energy. Correct? So, so that's a fundamental mechanism of how reactions happen. But what we are really focused on is the starting point. Okay. So A-B is a molecule, a C molecule comes in, then knocks off the A separately, and then the C combines with B, so that bond that is breaking, you know that bond dissociation energy has got some energy associated with it. So breaking of bonds has got usually it is an endothermic reaction, and formation of bonds is usually an exothermic reaction. So the net balance of A-B and B-C kind of tells you whether the reaction as a whole is negative or positive. So this is the reactants and this is the products. So when you plot the energy level of A-B and this one, so you have a starting level and then you have an ending level. So depending on whether the ending level of the products is higher than the reactants, or if it is lower. So this is reactants, this is products, this is reactants, this is products, correct? So depending on that, you term it as either exothermic or endothermic. Okay, and that is what is depicted by this energy diagram. So you have reactants on the left-hand side, the products on the right-hand side, and in this case, the products are on a lower energy level. So energy level is increasing this way. So if products are lower than reactants, I believe this is exothermic. Just verify it here. And the opposite is called as, this one is endothermic, because the delta H is positive, the products is higher compared to the reactants. So this is endothermic. Okay, so this is the reaction coordinate. Reaction coordinate is nothing but a fancy way of what stage of the reaction is it. So obviously it can be in reactants, it can be products, and now we're going to define this concept of transition state. Okay, and I'd already given you a hint. Typically we assume that the reactants always moves forward. So this is called as a forward only reaction or irreversible reaction. In reality, what happens is the reactants, as the reactants are forming new products, the products are again disintegrating back into the reactants. So that's why this is the forward reaction. This is the reverse reaction or backward reaction, whatever you prefer to call it. And eventually a state comes when the the reactants. So you're kind of, it's kind of a little bit of a goofy concept here, guys, because in this reverse reaction, the product becomes the reactant and the reactant becomes the product, right? So it's like, it's a reversible reaction, right? So the reactants are for moving forward in one direction to form a new set of products. But what I'm saying is that the products are also disintegrating to give back the original reactants, but in that reverse or backward reaction, the product becomes the reactant for that chemical reaction, and the reactants becomes the product for that second backward or reverse chemical reaction. Ultimately, what you do is you get reactants, and that's why you use this symbol, and this is called as equilibrium. In equilibrium, what happens is the rate of forward reaction, which is indicated by this forward arrow, half arrow, and this rate of backward or reverse reaction, as indicated by that bottom arrow, they kind of get in a balance, and no more reactants are getting converted to products, and no more products are getting reconverted back into reactants. And that's called as equilibrium. So we are going to start looking into that here, more from a theoretical concept, but I just want you to know that that is what happens in many of the reactions in reality. Rarely do you get a reaction that goes reactants going to products. I'll be honest in telling you that for the scope of this class, this is all you're going to learn about the reversible reactions or equilibrium. But for all practical purposes, understand that the reactants and products are in a state of equilibrium, or you can also call that as balance. Conceptually, are you guys on board?
Yep.
Okay. So now I want to introduce the concept of transition state. Okay. Ultimately, the delta H, or the heat of the reaction, which you call as the enthalpy change, that is always the difference in energy between the reactants and the products. Okay. So if the products are at a higher energy level than the reactants, this delta H is going to be positive, because the delta H is always energy of products minus energy of reactants. Okay, so if for an endothermic reaction, the energy levels are higher of the products, so that becomes a higher value, the energy of the reactants becomes a lower value, then delta H becomes positive. In an exothermic reaction, obviously, the energy level of the products is lower compared to the energy level of the reactants, and that's why you have a lower number minus a higher number, and that's why delta H is negative. Okay, so this is the concept of delta H that you're familiar with, right? Now let's define the transition state. A transition state is, what is happening is, when you're having two reactants A-B and C, okay, what happens is literally there is a transition, so you are not going to get this reaction instantaneously. Okay, so you don't get A plus B-C at the snap of a finger. So there is this transition where the bond between A-B is, and keep in mind, there are multiple molecules within this compound A-B and multiple molecules within the C. So gradually there is a transition, and at some point, if you kind of do a time lapse video on this one at a molecular level, you will see that you're going to have some of them A-B, you're going to have some of them like partially starting to break, some of them are completely broken, and then at the same time you're having B-C, and then you have the strong bond BC, correct? And then you have the C. So this is like called as the state of transition, and that usually on an energy diagram happens at the highest energy level, because there is a complete misorganization of what the energy from an energy, if you're tracking the energy levels of all of these different molecules, this hodgepodge, A-B on the verge of breaking down, then A-B completely broken down, C, A-C partially getting formed, B dash is the energy level is through the roof. That's why from when you track the energy level, this transition state is always going to be at a higher level compared to the reactants or the products. And the maximum energy in the maximum chaos level when that situation occurs is what you call as the energy of activation. Okay. So in other words, that's the maximum level of energy that you have to have being supplied for this reaction so that the reactions can go from the reactants to the products. So if you kind of look at it, if you guys have ever played with Hot Wheels, you know, and you set up your tracks, right? And you try to create a little bit of a mountain or a hill because you kind of like it, right? I mean, you kind of push it, right? From the starting point, you kind of give a flip to the car and starts going up. And sometimes what happens is you have to, you don't give it enough energy, it cannot go on top of that hill, right? That you created. But then once you create that hill, then it's instantaneous and then gravity kind of takes over. Are you guys able to relate to this example?
Yeah, that makes sense.
Right? So, and if you flip it not with enough power and then it just keeps going up and then keeps coming down, right? So you have to overcome that energy barrier, which is essentially defined as that maximum elevation that you're trying to overcome. And that's what this energy of activation, which we call as EA. Okay, so the transition state is this location. The top of the hill is called as the transition state. And at the transition states, pretty much everything, if you provide enough energy for that transition state for that reaction to happen, then you are pretty much ensuring that the reaction is moving forward. So the transition state is always located at the top of the energy hill that separates the reactants from the products. And this energy of activation that you require is called as E sub A. Okay. So the formal definition of energy of activation is it's the minimum amount of energy needed for a reaction to occur, because if you don't supply that minimum amount of energy, that reaction will not move forward. And then you're simply kind of trying to do, if you provide energy, if this is your this is your transition state, and you're only providing energy level to this point, whereas you need EA. So energy supplied is less than EA, reaction will not happen. If energy supplied is greater than energy of activation, reaction will happen. So the energy of activation is also basically the energy barrier that must be crossed. So now you're going to be looking at a couple of influence or effects of the energy of activation. The biggest one is the energy of activation determines the reaction rate, or basically how fast or quickly the reaction occurs. Okay, for a higher EA and a lower EA. So this one, the energy of activation is this hill, this is over here. So obviously what this is telling you is that the reaction can move faster. Reaction can move faster over here compared to over here. Higher the energy of activation, slower the reaction, lower the energy of activation, faster the reaction. So when the energy of activation is high, few molecules have enough energy to cross the energy barrier, and that's why the reaction is slow. When the energy of activation is low, many molecules have enough energy, because it's like, you know, what you would call as setting the bar low, right? If you set the bar high, then only few people can cross it. So that's why it's going to be a slower process. If you have a lower bar, then what you're doing is most average people can do it. And that's why there is a higher rate of reaction, or in other words, the reaction is faster. Okay. What else do we want to talk about? So this is the trend, and that exists for both a exothermic reaction and an endothermic reaction. Okay. So some takeaways. An energy diagram is a visual tool that helps to illustrate both the rate of reaction by the height of the. So anytime you see the rate, you are talking something over time, how quickly something happens. Okay. So a high energy of activation tells you whether it's a fast reaction or a slow reaction. Okay, it does not tell you anything about the relative energies of the states. So if I'm having an extremely high energy of activation, you do not know whether the reactants are at a higher place than the products, or the reactants are at a lower state than the products. The energy of activation in both instances is the same. Okay, so you don't know anything about the starting point or the ending point, but you do know that it's a slow reaction because it's got a high energy of activation. The sign of delta H tells you whether the reactants are lower than the product, or the product is lower than the reactants. So there are two takeaways. One is delta H and EA. So this tells you whether it is fast or slow. This tells you whether reactants are lower or products are lower. In other words, it tells you whether this is exothermic or endothermic. And generally, reactions are favored, means there's a higher probability of reaction happening in which the delta H is negative, and the products are lower in energy, making them more stable than the reactants. Questions?
Not yet.
Yeah, none for me.
All right, so let's look at some examples and then we will kind of switch some topics over, okay? Because there's a lot of contents that we need to cover today. So draw an energy diagram for a reaction with a low energy of activation and a delta H of negative 10 kilocalories per mole. The moment it says delta H is negative 10 kilocalories per mole, delta H is always the energy difference between product minus reactant. So if this difference is negative, you know that product is equal to lower, reactance is equal to higher. Okay, so what they're asking you to do is draw an energy diagram. Again, you don't have to be, it's all relative, right? So product is lower, reactant is higher. So you kind of do this, okay? So this is delta H, and just label this as negative 10 kilocalories per mole. Okay, and then this is your energy of activation. And they're saying that they have not given you a value, but they're saying that it is low. So it's again a very relative thing, right? So what I would do is redraw this, right? So this implies that this is EA is low and delta H is negative 10 kilocalories per mole. Okay, and then they're asking you to label the axis, the reactants, products, transition state, EA, and all those things. So this is reactants, this is products, this is transition state, this is EA, and then what are the axes? Forgot. Oh, energy is along this here. So reactants, transition state, low energy barrier, just call it out here, delta H, products, and then reaction coordinate, which tells you what state of the reaction that reaction is happening. So this is a very kind of a subjective answer. So if you guys don't get everything perfect in here, as long as you're able to illustrate that this is the concept of an energy barrier, if you kind of make this like this, you know, it's not going to be penalized against you, because I mean, just saying that low energy barrier, low is such a subjective thing, right? And if you're saying that this is delta H, but then now instead of this, if you're kind of doing this and say this is delta H, you know, at the end of the day, it's all relative. I'm not going to be worried about it. I just want you guys to kind of demonstrate that you have understood the concept. Have you?
Yeah, I think it'll make sense once we have like an example, like.
Right, but no, you understood the theory
Yeah.
portion, right, Drew?
Yep.
Okay. Brian?
Yeah, got it.
Okay. All right. Now, trying to see what else is there here. Okay, we're going to talk about catalyst. Okay. Okay, So now, before we define the concept of catalyst, let's look into reaction rates. Okay. You guys observe this in many aspects of our everyday lives, right? Aspirin is one of those painkiller. What it essentially does is it goes and blocks the synthesis of pain-causing molecules. So when you are having a headache, your body produces certain molecules that are by nature, by principle, kind of pain-causing, correct? And what aspirin does is basically goes and neutralizes the effect, and it blocks the synthesis of that. And in things like that, would you agree that you want something, you don't want 2 hours before your medicine kicks in? Would you guys agree? You want something that is instant. Fair? So aspirin is one of those things that you want it fast. Okay, so that chemical reaction of neutralizing the synthesis of the pain-causing molecules is something that you want it fairly quick. In other words, it's something that you want the low energy barrier, and you want that reaction to be as quick as possible so that you are getting relief from the pain. On the other hand, butter, okay, when you leave it out on your countertop, okay, believe it or not, most people don't even realize it, but if you leave it, I mean, try leaving a small piece of butter on at some place in your house, and then just leave it untouched for about 1 month. And you'll come back and you'll see that the butter has completely transformed, and the fat molecules are getting slowly oxidized by oxygen, right? To really nasty, gross looking, moldy butter that you'll not be able to taste, but it looks horrible, okay? You don't want that reaction to happen quickly, because then that means now you're imagine that thing was to happen quickly like aspirin. Now, how do you consume butter, right? In your toast and in your food. You want that reaction to be as slow as possible, correct? Whether you want it or not, that butter getting oxidized to a rancid or to a undesirable form is going to happen. What you want to do is control that speed of the reaction. Okay, so some of the reactions are beneficial when they're fast. Some of the reactions are beneficial when they're slow. Some of the reactions are harmful when they're fast. Some of the reactions are harmful when they're slow. So depending on the application, you want to control the rate of the reaction as much as you can. Are you guys understanding the concept of why the reaction rate is so important?
Yep.
Okay. So, and that's where the energy of activation, the minimum amount of energy, is very fundamental characteristic of a reaction. And some reactions are fast because of low energies of activation. So let's look at another practical example. So the combustion of gasoline to form carbon dioxide and H2O. So we keep talking about combustion of any gasoline, right? So gas plus oxygen gives you CO2 plus H2O. And you know that this has got a huge delta H negative value, which means energy is released. Okay, so you do know that by itself, you're never going to have a combustion reaction, right? That's why when you turn on the ignition of your car, what do you think you are doing? This reaction has got a huge amount of energy of activation. Okay, when you ignite a spark plug, what you're doing is you're creating that high level of energy instantaneously to overcome this thing. And once it is started, the reaction is started, then it is self-sustaining, and that's how you get combustion reaction. So in this case, the EA value is high, and it is a very slow reaction. If you don't do anything, in fact, the reaction won't even start. So that's why you need that spark or that flame to initiate the reaction. Anytime you take a lighter and turn on the burner, what you're doing is you're creating a spark, and that spark allows you to overcome that energy of activation. Okay. So there's some theory here, which I'm going to skip here. You guys can read through this. As a general rule of thumb, a reaction rate doubles for every 10 degrees centigrade the temperature is raised. Heat is usually a very good accelerant for any chemical reaction. Again, goes back to that baking example. if you try to bake a cake at 100 degrees, it's not going to happen. If you're going to try to do it at 200 degrees, it will bake very slowly. It'll probably take about 2, 3, 4 days. You don't know. If you try to do it at 250, you might be able to do it in about 6 to 12 hours. If you do it at that optimum temperature of 300, 325, you'll get a cake in about 45 minutes. So what you're doing is, for every 10 degrees centigrade that you're raising the temperature, you're basically doubling the reaction rate. Okay, and the inverse is also true. Every time you reduce the temperature by 10 degrees, you're generally cutting the reaction rate by about half. Okay, so now I want to get into the concept of catalysts. A catalyst is nothing but a substance that speeds up the rate of a reaction, right? We talked about this on Tuesday in the introductory portion. But technically, and in a scientific manner, what it does is a catalyst accelerates a reaction by lowering the energy of activation. Okay, so again, keep in mind, anytime we talk of energy activation, EA, you're not talking about the relative energy levels of the reactants and the products. All you're talking about is this energy barrier or the height of this hill. So if you pay close attention here, you will see that this blue graph is basically the reaction without the catalyst. That's why it's called EA uncatalyzed. Okay, this lower one is EA catalyzed, and what that means is the catalyzed one, because you add that catalyst, you are dropping the energy of activation, and as a result, you're getting a faster reaction compared to the uncatalyzed one. Okay, so that's the basic concept and premise of a catalyst. It basically lowers the energy of activation and it speeds up the reaction. Okay, the good thing is the starting point and the ending point are always the same. When you add a catalyst, it doesn't change the starting point or the product, and that kind of tells you one very fundamental characteristic of a catalyst. Oops, what happened there? Okay, a catalyst does not participate in the reaction. Think of the catalyst as more like a moderator or a mediator. All it tries to do is facilitate, but it does not get into the relationship of the 2 or 3 entities by itself. It just influences the outcome and allows them to get to their destination in a more controlled manner. What I'm trying to say is the catalyst does not partake in the reaction. And there are several examples of this. Metals are very commonly used catalysts in reactions. Okay, so we looked at ethylene, which is CH2. Okay, sounds good, Brian. Ethylene does not react with hydrogen, but in the presence of palladium, a rapid reaction occurs and ethane is formed as the product. Ethane is a fuel. Okay, so what this is saying is that if you have CH2 plus hydrogen, and you are not going to get anything reaction, so nothing gets formed here. But the moment you do CH2 plus hydrogen and then add a catalyst, which usually is put on top of that arrow, in this case the catalyst is palladium. Okay, now you're going to get a reaction CH3, and you get the reaction and form the product. This reaction is named as hydrogenation, and this is used as one of the most common reactions in the food industry to prepare your margarine or peanut butter and many other forms of cooking oils, vegetable oils, things like that, anything that is fatty. So if you do not use this catalyst, in other words, this reaction, the reaction 1 without the catalyst would look something like this. But when you add the catalyst, it would look something like this. So you're basically dropping the energy of activation, and the palladium does not get consumed in the reaction. The palladium stays as it is. But the catalyst, all it does is that it facilitates or accelerates that reaction by lowering the energy of activation. Another very common one in terms of catalysts are what we have in our bodies, which are called the protein molecules called the enzymes. These are nothing but the biological catalysts that help us for various organic reactions. Let's look at a few examples. Okay. So lactase, not lactose, but lactase is the enzyme that binds the chemical lactose, which is essentially the principal carbohydrate in milk. So when you consume milk, the carbohydrate there is in the form of lactose. Okay, but the carbohydrate, the lactose carbohydrate, is binded or held together by this enzyme or protein called as the lactase. Okay, so what happens is once it is in the bound form, the lactose is converted into two simpler sugars, glucose and galactose. So the reaction is basically lactose, the carbohydrate, getting converted to glucose and galactose. Okay, the problem of lactose intolerance is essentially when the individuals do not have this enzyme, correct, the lactase enzyme, they're unable to digest the lactose, and lactose by itself is what causes that irritating and uncomfortable feeling of abdominal cramping and diarrhea. So when someone is having lactose intolerance as a condition, it is mainly because they are not able to produce that enzyme or the protein which is used as the catalyst to enable this reaction to occur, which converts the lactose from which converts the lactose to glucose or galactose. Glucose and galactose are simpler molecules, and most people can process them in their bodies, and it's not a problem. The problem is if you don't have that enzyme, if you don't have that protein or that enzyme, you're not able to have that reaction, and that's results. That is the cause of lactose intolerance. Okay, so this lactase is basically nothing but a biological catalyst, which most of us have, but for people who don't have that enzyme, that reaction cannot happen, and that's the reason why some people are lactose intolerant. Okay. Then let's look at one more example. We talked about catalytic converters. Catalytic converters are basically nothing but, again, the word catalytic means it is basically, it has got a catalyst. And what this does is actually this thing. You know, usually the catalytic converter usually has a metal catalyst, in this case, rhodium, platinum, or palladium. Okay, and those are the three catalysts which convert this reaction and make them happen, which is basically taking an CXHY in the general form plus oxygen, converting it into carbon dioxide and water vapor. Okay, and if you remember from back in the day in the 1970s, during this combustion reaction, when you burn fuel, you certainly produce carbon dioxide and H2O, which are generally considered harmless. But when you don't have the reaction getting completely consuming the gasoline molecules, which is generally carbohydrates, hydrocarbons. That's why it's CXHY. The CXHY can be many different things. It can be C2H6, it can be C3H8, it can be C4H9, so on and so forth, right? Different kinds of fuels, or it can be CH4, which is methane. So if you have unreacted gasoline molecules that come out on the product side, what happens is those are toxic. In addition to that, when you burn a fuel, usually you want carbon dioxide and water vapor. Okay, but what happens is sometimes you get carbon monoxide, and you both know that carbon monoxide is an extremely toxic compound. In addition to that, some of the fuels have got a nitrogen element, and when nitrogen is present, it combines with oxygen to form nitrogen monoxide. This nitrogen monoxide plus H2O, which you're forming from this combustion reaction, gives you HNO3, which is nitric acid. So what the catalytic converter does is it makes sure that these combustion reactions are completely getting converted and there are no unreacted gasoline molecules. They also make sure that carbon monoxide gets converted to carbon dioxide and nitrogen monoxide, NO, gets converted to nitrogen dioxide, which is harmless. So nitrogen monoxide, carbon monoxide, and unreacted gasoline molecules are not good. So all the catalytic converter does is it gives it extra space and extra time, lowers the energy barrier so that all of these reactions can get completed the way they should do. So this was a big problem back in the 1970s and 1980s when incomplete combustion was leading to inefficient utilization. And when that gas crisis happened, people were like, really, well, I'm not getting complete combustion, so I'm not getting the full efficiency of it. So that's where they introduced this concept of catalytic converter, which helped make sure that the unreacted gasoline molecules is minimized and all the toxic byproducts that typically come from incomplete combustion, they are taken care of. And that's why catalytic converters were a big deal back in the 80s and 90s. These days, the engines are much more efficient. They don't let these things happen. So that's why most cars, I think, still come with a catalytic converter, but I don't think it's as big of a deal as what it was back in the day because of technology development. Okay. Question?
Nope.
Brian?
Yeah.
Okay. Want to see what do we want to cover here? Oh boy, this is all these things here. Okay. I might be making a judgment call here, guys. Let me just check something. Bear with me here. Okay. So I'm going to ask you guys, I mean, this concept of equilibrium, there's a ton of concept here. I don't want to rush it through. I don't think we'll be able to get this thing done in 45 minutes. What I'm suggesting is that we skip over this topic and we don't cover this in this term.
My vote's yes.
What's that?
I said my vote is yes. Skip it.
Yeah, because the problem, guys, is that, I mean, if we start this concept in terms of a balance, the problem is it has got building effects in some other aspects. So, okay, why don't we at least get some exposure to this, and maybe we won't get into the full details of it, but at least I want to kind of introduce the concept to you. I promise you will still kind of stop at 7 o'clock. How about that?
Sounds good.
Yep.
Okay, because the problem is, I mean, it's not, so we will try not to make it too complicated, but at least I want you guys to get some basic concept, right? We already talked about equilibrium, right? The reaction is basically reversible. And that's why there's two full-headed arrows. For example, carbon monoxide reacting with water, the forward reaction goes from left to right, and the reverse reaction, usually indicated in the bottom, goes from right to left. Okay, so we already talked about those things. Okay, so forward reaction goes from left to right, reverse reaction goes from right to left. Okay, the equilibrium is basically when so this is kind of a molecular graph here. So if you look at this, so the reaction is basically A going to B. Okay. So you see these blue spheres, 1, 2, 3, 4, 5, 6, 7, 8. The red is the product, which is the B, right? So here you have 6 blue and 2 reds, and then you're eventually reaching to 3 blues and 5 reds. Okay, this is just a made up random example to kind of illustrate the point. But once the reaction is happening, you see that these 5 red spheres are maintained and the 3 blue spheres are maintained. So one key thing to remember is the reaction rate of the forward, which is, say, let's call RF, is equal to the reaction rate of the reverse. Or you can say RR is equal to RF. So keep in mind, it does not mean that the reaction, the forward reaction or the reverse reaction have stopped. All this means is that once you reach the equilibrium, so this is the point of equilibrium. What this is saying is that the blue sphere is still getting converted into the red, but the red sphere is getting converted back into the blue. So forward reaction is getting converted, forward reaction is the same as the reverse reaction. And that's why you reach the equilibrium. So when do you know that you have reached an equilibrium? When the net change in the number of molecules of the reactants and the products is equal to 0. So that means that the blue is getting converted into red, and the red is getting converted back into blue. So that's why you're trying to say that the rate of forward reaction is the same as the rate of a reverse reaction. Okay, so generally, this is some of the concepts I want you guys to take away, because we're going to be using this equilibrium constant. So if you generically depict any reaction, number of moles of A, and so let's talk. The reactions is basically A plus B. Forward reaction gives you C plus D. Okay. So 2 reactants, A and B, are combining, 2 products are formed, C and D. Okay. Now you're indicating the number of moles, and this is in a very generic manner, A, B, C, and D. Okay. They represent the number of moles or coefficients in the balanced chemical equation. Okay. So far, so good, guys?
Yep.
Okay. So now, this is what I really want to define. It's called the equilibrium constant K. For this reaction, once it reaches equilibrium, that equilibrium constant K is nothing but the concentration of the products, which is indicated by these square brackets, okay, raised to the individual coefficients of those 2 products, divided by the concentration of the reactants, raised to the individual coefficients or number of moles of that. So this equation is very important when you're solving problems related to stoichiometry. So the equilibrium constant K is defined as the concentration of products in general, divide that by the concentration of the reactants. But how do you actually mathematically do it is concentration of product number 1C, which is always indicated by this square brackets. This means concentration, and you will see pretty soon here that concentration is nothing but moles per liter. So this raised to the power C, which indicates the moles of that product, and D, capital A and capital B. Okay, so let's look at an example. So nitrogen gas reacts with oxygen. Forward reverse reaction gives you 2 moles of NO. So the equilibrium constant K for this is nothing but the concentration of NO raised to the power 2, y to the power 2 because of this coefficient 2, or the number of moles of nitrogen oxide. Divide that by the concentration of nitrogen, divide that by the concentration of oxygen. So these are the reactants. These are the products. Okay, but keep in mind here, raised to power, the reactants, both of them has got 1. So that's why you have nitrogen concentration raised to the power 1. So write the expression for the equilibrium constant for the following balance. You can always make sure that the reaction is balanced, okay? So 2 times CO plus oxygen gives you 2 times CO2. So the equilibrium constant K is nothing but concentration of CO2, square brackets, raised to the power 2 because of this coefficient 2 or 2 moles. Divide that by the concentration of the reactants. So this is the reactants, this is the products. So again, concentration of reactant number 1, CO, raised to the power 2 because of this 2, times concentration of oxygen to the power 1. So you can just leave it as it is. So that's how you get this CO2 to the power 2, divide that by CO to the power 2 times oxygen to the power 1. Why is this equilibrium constant important? Okay. When the equilibrium constant is a value that is much, much greater than 1, okay, and we'll look at some examples. So this is just called as K greater than 1. But when you want to say that this is much, much greater than 1, you kind of emphasize by using this greater than symbol. So if the equilibrium constant is significantly greater than 1, what this tells you is that the equilibrium lies to the right and favors the product of the favors the formation of the product. In other words, K is nothing but the concentration of products over reactants. So if this K value is significantly great, if K value is equal to 1, what does this mean? The concentration of products is equal to concentration of reactants. Do you guys agree? Yes, no?
Yep.
I don't know if you heard me.
So what happens is, if the K value is significantly greater than 1, the numerator is greater than the denominator, and the numerator being products, what you're trying to say is that the equilibrium favors the product, or in other words, the equilibrium favors the right-hand side. Okay. Obviously, if K is significantly less than 1, which is indicated by this equation, now you know that the products is going to be significantly less than the reactants, or in other words, the equilibrium is shifted to the left-hand side. When K is less than 1, the denominator is larger, the bottom one, equilibrium favors the reactants. When the equilibrium constant is around 1, anywhere in the range of 0.01 to 1, then you can generally say that both reactants and products are present roughly in the same concentration. Okay, so let's look at an example, and this will hopefully illustrate the point. The equilibrium constant for the reaction of hydrogen and oxygen to form water. So the reaction is 2 times hydrogen plus oxygen. Balanced chemical equation gives you 2 times H2O. So the K value in this case is given to be 2.9 times 10 to the power 82. Okay, so this, I'm going to say that 10 to the power 82 is significantly greater than 1. Do you agree?
Yep.
Okay, and because 10 to the power 82 is, keep on doing this, this is the number. So this is significantly greater than 1, right? So what this is saying is that anytime you bring hydrogen and oxygen together, you're almost guaranteed to form the water molecules. You're not going to have much of the reactants unreacted. The products are going to be dominating the reaction. which is exactly what you want. On the other hand, the equilibrium constant for the conversion of oxygen to ozone is much less than 1. Look at this value. The K value, equilibrium constant, is 2.7 times 10 to the power negative 29. Would you guys agree that this is significantly small?
Yes.
Okay. And that implies that this reaction, you are going to have oxygen dominating compared to the formation of ozone. Almost no product of ozone is formed. Okay. And the reason why this is so important is you guys have heard about the ozone layer, correct? If this is your Earth, no, this is the Earth is over here. So you know that, oh gosh, why am I struggling here today? Okay. So if this is your, where you and I, we all live here, right? I mean, this, I think this is called as the stratosphere, right? You have heard of this ozone layer, haven't you?
Yes.
And this is what protects us from the harmful UV radiations of the sun. The beauty of this thing is this ozone layer is actually free because oxygen is there in the stratosphere that we are all breathing from. But because of the energy coming from that sun, this normally this ozone getting oxygen getting converted to O3 is not happening because you don't have as much energy. But the higher you go, you have the perfect form of the energy to overcome this activation energy for this ozone getting converted to oxygen getting converted to ozone. And that's why you get the formation of this ozone layer, which is very critical for our survival. Because if this ozone layer were not existing, we would all be toast. And this ozone layer is what gets destroyed in terms of the greenhouse gases. That's why we want to minimize these greenhouse gases so that you're protecting this ozone layer. But from a chemical reaction standpoint, what is happening is normally you have oxygen getting converted to O3 according to this reaction. But unless you have the right environmental conditions and the energy available to do this, you don't want to happen. Otherwise, all of this oxygen that we are wanting to breathe for ourselves, for our respiration, if everything gets converted to ozone, you and I, we cannot breathe ozone. We are only able to breathe the oxygen. So that's why this delicate balance of nature is designed in such a way so that the oxygen does not get converted to ozone at the lower levels, but it does it at a higher level where it serves a very specific layer of a very specific purpose of protecting us from the UV rays. Okay. So we'll looked into this K greater than 1, equilibrium favors the products, equilibrium lies to the right. K less than 1, equilibrium favors the reactants, equilibrium lies to the left, and K roughly equal to 1, both the reactants and products are present at equilibrium. Okay, so I'm going to skip some of these things. Few more points. There is no relationship between the equilibrium constant and the reaction rate. The reaction rate is strictly a function of the energy of activation. That is the only impact of the reaction rate. But the equilibrium constant just tells you how much of the reactants is there versus how much of the products is there. So when you keep tracking of K, delta H, and EA, okay, they all kind of serve three different functions. K tells you which way the reaction is favored, whether it's reactants, products. Delta H tells you whether you're absorbing energy or releasing energy, what is the relative energy levels of the reactants and the products. EA tells you how quickly that reaction happens, has no bearing on where the reactants start in terms of energy levels or whether how much of the reactants or how much of the products. So they are all three different factors indicating three different aspects of a chemical reaction. Okay. Okay, so I think I'm going to skip some of these things. You guys get the idea here. So this is a fun little thing. I'll just kind of cover this. So you have this reaction A going to B. The equilibrium constant is basically 10. So you know that K is nothing but the concentration of products over concentration of reactants, right? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you have 11 molecules of A, okay? You know that the equilibrium constant for this reaction is 10. So 10 is equal to concentration of products over concentration of reactants. And once you reach equilibrium, this you can say that products is nothing but 10 times reactants. So if you were to indicate the product to be a different color of red, you know that at equilibrium, you should have 10 times more number of molecules compared to the reactants. That's what this is indicated in terms of the graphical art. K is equal to 10 times 10 over 1. Or in other words, say if the product is indicated by the red spheres, which is indicated by B, okay? B is the product here, A going to B. You're going to have 10 times more molecules than the reactants at equilibrium. Does this make sense?
Yep.
Okay. So concentration is usually indicated by, I wanted to see if here, yeah, that's why, because we're going to get to concentration. Okay, so we'll introduce the concept. We're going to spend an entire chapter on concentration for solutions, but generally concentration is nothing but number of moles per liter. So liter is a unit of volume, and you know that moles is nothing but number of moles can be converted into the mass. Moles times the molar mass. So this is moles times kg per mole, which is the molar mass. The moles and moles gets canceled and you get kg, right? So moles is nothing but an indication of quantity. So how much quantity is there in a given volume is essentially what you're representing by this moles per liter. And in chemistry, there is a symbol for that called as capital M. So M is nothing but moles per liter. And it's a unit of concentration in chemistry. So how do you apply that? So again, keep in mind concentration of any compound is basically that compound put within the square brackets. So this indicates that this is 0.25 molar or moles, which is nothing but 0.25 moles per liter. What this means is that if you have a jar that is 1 liter, the concentration of this is 0.25 moles of A. Okay, concentration of B2 is essentially the same 0.25 moles, and the concentration of AB is essentially told as 0.5 capital M or 0.5 moles per liter. The reaction is still happening, is A2 plus B2 gives you 2AB. So now the equilibrium constant is concentration of products, divide that by concentration of reactants. So product is AB, but then don't forget the square because of this 2 moles here. Divide that by concentration of A2, but since there is only 1 here, you can ignore that. B2 to the power 1. Now they've given you the values of the concentration, so you can get 0.5, don't forget the square, 0.25 times 0.25. And when you do the math, you'll get the equilibrium constant as 0.5 times 0.5, divide that by 0.0625, and you get the answer as 4. So the equilibrium constant for this reaction is 4, which I wouldn't say is significantly greater than 1. It is somewhat greater than 1, or in other words, this reaction A2 plus B2 gives you 2AB. You're going to have about 4 times concentration of the product AB compared to the concentration of A2 and B2. Okay. So similar kind of example. Calculate K for the reaction of N2 and H2 to form NH3. So always write the reaction N2 plus 3H2 gives you 2 NH3. You guys know how to balance a chemical equation. So now K is nothing but NH3 concentration. Don't forget the square. Divide that by concentration of nitrogen to the power 1. So you can ignore it. But hydrogen, you cannot ignore it because this is 3. So this is the formula for chemical equilibrium for this reaction. Now for ammonia, the concentration is given to be 0.12 raised to the power 2. Concentration of nitrogen is given to be, nope, I was wrong there. Concentration of ammonia is given to be 1.1 square. Concentration of nitrogen is 0.12. Concentration of hydrogen is 0.36, but hydrogen to the power 3. When you do this math, you'll get the equilibrium constant as 216. So 1.1 times 1.1, divide that by 0.12 times 0.36 times 0.36 times 0.36. When you solve this mathematically, you'll get 216 rounded to 220. So this, I would say, is significantly greater than 1. In other words, you're going to have 220 times more formation of products compared to the reactants for this chemical equation. Okay, so similar kind of thing. Le Chatelier's principle. Yeah. Okay, I am going to do something, guys, here. I'm going to I think this probably, it's important that we cover this chapter. Why don't we pick it up on Tuesday and finish up this chapter? And then we'll see, we'll kind of have to adapt how we want to do this. How does this affect the other chapters? Because I think I want to stop here. This might probably be a good stopping point. So why don't we try picking it up from Le Chatelier's principle on next Tuesday, and I'm going to try to repurpose something here and cut the content from some other chapter. Are you guys okay with that?
Yeah, sounds good.
Yeah, it's perfectly fine with me.
Yeah, because I don't want to, I mean, I know you guys learned a lot of new concepts, especially the concentration and things like that, but it was not outrageously bad, was it?
Yeah, a lot of it seems like it's just plug and chug. Like I don't.
Yeah, hopefully you guys got the concept of the energy diagram and you guys got basic principles of equilibrium constant, right? That's what I want to hear.
Yeah.
Okay, so let's stop here and then let's pick it up on Tuesday and then we'll see how it goes. I certainly don't want to overwhelm you guys, but at the same time, I'm struggling to see which content to drop here. Okay, we'll figure it out next week, or I might do it. I might do it this weekend, and then we'll talk about it on Tuesday. And I promise you, your grades will be done this weekend.
Yeah.
This has been a rough week. This has been a rough week. So
It's all good.
Well, see you next week.
okay, have a good weekend, Drew.
And I will see you in a bit.
Later, guys.
I promise you, Brian, you hopefully it won't be too bad for you.
Yeah, I remember you saying Tuesday that it wasn't gonna be too bad. So I'll see you then.
The problem is, I mean, like I have the luxury of like, I mean, literally, I mean, like I'm dragging out the math course, but in chemistry, I wish I had one more lecture available. And I'm really sorry, guys, that I'm kind of struggling, which content to draw because this chapter is really, really important.
Okay.
So we'll figure it out. I mean, at the same time, I hope you can appreciate that I didn't want to stress you out more than what I did.
I do really.
Sounds good. So, well, enjoy your break, grab some dinner, and then we'll see you at 8 o'clock for
Sounds
a quick
good.
for a quick one. See ya.